This is a project done by the University of Portland Robotics Club, taken into a multidisciplinary senior design project. So in 2010, Tim Vanderwerf, at the time was a junior, and he founded the Robotics Club looking to get some more hands-on project multidisciplinary work done here while he was a student. So I'm just going to give you some background of how I got involved and then sort of how the project evolved from that. So I got involved my freshman year, which would have been his senior year, when we built the second generation robotic mining excavator, which was just a simple four-wheeled H-frame bucket excavator, kind of like a bobcat. So we've been participating since 2010. We've built 2 different types of devices. The premise of the competition is we want to go off of Earth, right? We want to establish human colonies on places like the Moon and Mars, but we realize that those are expensive endeavors, and so we're looking for strategies to reduce those costs. One of the major costs in establishing an extraterrestrial human presence is actually creating a habitat for humans to live. Currently it's about $1.5 million per kilogram to put something in space. So if you add up all the things you touch on a daily basis, you can see it gets kind of expensive. So one of the cool strategies we're trying to utilize as a race, I guess, is called in situ resource utilization, or living off of the land. Kind of what the pioneers did as they were pushing west. And the idea is, if I can save myself the effort and the cost of shipping all of my needs and habitat requirements to Mars, if I can build that using resources on Mars, I can cut out that cost, which is actually quite a bit. So NASA started this competition in early 2010 saying, hey, we've got university students who are itching for hands-on projects. We've got this big problem that needs to be addressed if we are going to make our way into space. So let's have a competition. So NASA provides a sandbox. It's about 24 feet long, 8 feet wide, and is filled with a flour-like basalt powder that's about 3 feet deep. And each university team is to build a robotic excavator that would perform operations as if it were on a different planet. You're looking here at what we've determined our transport robot to be. Sort of the first thing, I guess I'll sort of walk you through how we designed it and then walk through each system as we designed it. Traveling over the terrain is kind of a difficult task. NASA puts obstacles in the arena for us to drive over. 2 of those being rocks about a football size in diameter and pits about the equal size in removed material. So we have to sort of either avoid them or drive over them. And we decided to go with the rocker bogie suspension system. So rocker bogie was a system designed by NASA JPL engineers when putting rovers on Mars. So it's featured on MSL, Curiosity, Opportunity, that sort of stuff. And it's claimed to be able to drive about a wheel diameter in height. So a couple key features are large wheels. So these are about 1 foot in diameter, 30 centimeters. And that'll allow us to climb obstacles about 1 foot in height, which is bigger than a football. The idea is we can go over the obstacles. But then, as the name says, it's rocker bogie. So you've got a rocker arm here, which is attached to the frame. And then at the front part of the rocker, you have a bogie. And what this does is allow for more points of contact on the ground at all times, as opposed to 4-wheeled suspension systems. The other key feature for a rocker bogie suspension system is its differential averaging system. And that's what you see here with this tube geometry and then this bar in the back. So this allows the device to stay more or less stable as it does traverse over obstacles such as craters and rocks. So if I were to, say, run over a rock with this rear left wheel, you'll notice that this wheel is popping up. And as it is doing so, it is pushing this rod forward and turning the differential system. And what that does mechanically is exert more force on the right side of the robot and try and right it. As if I'm going over the rock, it's going to want to tip to the right, but if I apply more force over here, it exerts a moment reversing that, and ultimately keeps the frame level. This is really important. If we're carrying a lot of material, we don't want to lose that while we're transporting it. But also we're going to be deploying our excavator device, which I'll talk about at a later point in time. And we don't want to drop or flip over prematurely while driving over that. it's really important that we deploy the device instead of having the two drive out together, because it allows us to remove a complicated suspension system from the excavator and make it that much more tailored to excavation. So that's what you see here with this winch and conveyor belt system. We like the conveyor because it provides for two modes of operation, discrete and continuous. So I can turn the belt halfway or a quarter or all the way around, or I can run it continuously, whatever the operation requires. And that's really handy because in timed environments, specifically for the competition, we only have 10 minutes. So say each run, each collection run takes 3 minutes, right? I could get through 3 cycles and then have a minute left over. I could cut short a cycle by using the discrete operation versus the continuous one, and that would get us more material in one time. Additionally, using the conveyor belt also allows us to gradually deploy the excavator. We really don't want the excavator to flip over or poorly deploy, as that would be mission critical failure. So those were sort of some design considerations when we created the conveyor belt. And then, having decided on using a conveyor belt, we wanted to come up with a system that would allow us to not only deploy the excavator, but receive and deposit material at varying heights. And so we said, what sort of systems exist in the world today? Winch, elevators, lifts, things like that. The last two on that list are rather complicated and somewhat weight intensive. NASA restricts our maximum weight to about 80 kilograms. So we decided to go with a winch and cable system. So that's what you see here. You have two collaborating cables going back to a common winch drum in the back here. And when necessary, we can actuate that motor to raise and lower the conveyor belt as we need. So that's a pretty good summary of what's going on here. One thing I failed to mention earlier about the suspension system is that the wheels articulate. NASA says, shipping things to space is not only expensive, but but volume intensive. So we have to be very specific about how we allocate weight and mass to the robot to help us sort of refine our robots. They say, our maximum build volume is 30 inches wide, 30 inches tall, and 60 inches long. So our entire robots, I guess you'd say, have to start in that box to begin. And so these wheels actually articulate 360 degrees, and we named the system the articulation joint for that very reason. But this allows us to pack our wheels underneath, and then once the competition begins, we will spin them out 180 degrees, effectively almost doubling our wheelbase, helping us prevent hazardous tipping events, as well as allowing this conveyor belt to actually hit the ground when we need it to. So that's sort of a basic summary of what's going on here. As far as electronics in the back, we're using lithium polymer batteries because they're relatively energy dense, and then military grade hardware for distributing electrical power to the systems that require it. As I was talking earlier, the club itself has been running since 2010, so I think you could argue that since the club started, this mining robot idea has been ingrained in the heads of several students. But I don't think we actually got on the idea of more than one robot until, what was that? May of 2013, so about 2 years. We decided to take a year off, our junior year, I guess, to sort of reevaluate the competition. What's going on? What's NASA really looking for? Are they awarding points to the winning teams because they see innovative strategies, or is it purely because they excavated the most material? If we were actually on Mars, would these systems really work, or do they take advantage of something on Earth that doesn't exist on Mars and they really aren't feasible? So that was most of the first semester, junior year, and then second semester we started working on preliminary designs. We really wanted this to be autonomous because when you're on Mars, at least when the device is on Mars, you aren't going to be there to control it, and controlling from Earth is already a huge feat in that it's about a 40-minute round-trip signal delay. So if your robot is doing something potentially dangerous, it would take 20 minutes for you to say stop, and then another 20 minutes for the robot to confirm its status, and by that time it would be an hour before you could send a secondary signal. So that's not really feasible, especially in high energy mining environments. Unfortunately, we're not going to be able to get there, but we identified the need for a testing facility. So we wrote a proposal to the dean of the engineering school, as well as the provost and the vice president of operations. We worked with Mr. Paul Ludi in facilities planning, saying, hey, here's this need. We think this is really important for us to be able to do this project correctly. How can we go about it? Here are things we need for this to work. What can we do? And we were lucky enough to actually secure a space in Haggerty's parking garage. So if you're ever walking in Haggerty parking garage, you see a sort of a wooden box on the Willamette side. That's the test facility. So while we're not going to be able to do autonomy this year, there's going to be another senior design team next year headed by Jamie Sears. He'll be a senior electrical engineer, and he's actually going to take this system and take it from manual control to autonomy. A lot of people have been talking about senior design presentations lately. We were lucky enough to have Darlene Shiley, for whom the School of Engineering was named, here in the audience for our presentation. She was kind enough to actually fund a LiDAR unit for us that we'll be using for that project next year. Robotics is cool. We'd love to get people from outside the engineering school involved. It's a lot of, especially a project this size is really tough to manage as well as engineer. So looking to people who are interested in fundraising or project management, things like that, marketing, advertising, that would be really cool to have. I know we definitely wish we would have had some this year. Other than that, robotics is awesome. It's a great place to learn things you never thought you'd learn and get exposure in fields that potentially you might pursue later on. So.
What should people do if they're interested in joining robotics or helping out?
Attend a club meeting is actually a good one. They should be setting up a schedule, so get on the email list of the activities fair next year. Another direct way would be email Jamie Sears. He'll be, I believe, the president of the club as well as the team lead for this project as a senior design team. So his email is searsj16@up.edu. So send him an email. I'm sure he'd be delighted to have some more support. Yeah.